के प्रॉमिस करदा मैं लड़ांगा तू फैन सलमान खान दी ओदे गाने गा के मैं तेनू बढ़ाऊंगा. Oh hey everybody. Hi. Whew. Okay. Ah, bug. Haha. Anyway, so we are doing medium problems right now. Oh, I forgot to do these. I actually got a phone call and got sort of busy after that. Okay. Hmm. So power function. So we've been asked to implement the power function. So the n answer is to multiply x n times. Can you think of something better? There's actually, okay, I'll give you a second to think about it, yeah? If you can think of how you can do something better than on. Okay, so I'll give you a very simple hint. What general runtime do you know that is better than n? So there's n cube, there's n square, there's n log n after that. After that there's n, and after that there's log n. So, and we all know. So okay, let's consider that we have to solve this in log n, right? So we all know that how do we do things with log n? when does the algorithm have something in log n? It's usually when we do binary search. So what do we use binary search for? Um, you might think we use binary search for finding a number in a sorted array. But if you try to think of binary search as an algorithm instead of a method to find a number in a sorted array, you might figure this out. So what binary search actually does, apart from finding a number, is that it reduces your answer space to half, right? Which is why you get the log n answer, log n complexity. And while reducing your answer space to half, uh, you're doing half the calculations every time, right? So you're gonna think, so if we reduced our answer space by half and we have to do half the calculations, uh, how does that help us? So if you look at it at as changing it just once, you'll it'll not look fruitful. But what's it doing? What you essentially have to do in calculating the power is multiply it once, then once again, then again and again and again and again, n number of times. So what if and if you if we in an earlier lesson we learned something that every number can be represented as the power of 2, right? So the trick here is that we don't actually have to do it n times, because since you can represent n as a power of 2, uh, and so basically how what x to the power n converts to is say, depending on what n is, let's just take an example for making it easier to explain. So it might be say n square or n cube, which you can also write as n square plus sorry, n square times n, or if it's say n to the power 4, which you can write as n square into n square, or say n to the power 5, which you can write as n square times n square times n. So if you notice, we are using n square again and again. Similarly, if it was x to the power 8, that would be x square into x square into x square into x square, which can also be written as x to the power 4 into x to the power 4. So what, say if it was 9, then it'd be uh, x square into x square into x square into x, which would be x to the power 4 into x to the power 4 into x. So basically, you might need to use you might, which is like x square into x to the power 0. So hence representable as a factor of 2. So hence you might be realizing that how similar to how we used x squared twice, every factor of 2 will be used twice for greater numbers, and we won't really have to calculate that number twice. So if you already have x to the power 4, you can just use that again. And you won't even have to save it. What we would be doing instead is just, if we know that our number is going to be using that, we'll just use it then and there. So it will not be exactly log n, because for say an even number, sorry, an odd number, or even an even number, where all the factors don't come together. So say if it's x square into x to the power 4 into x to the power 8 into x power sorry, yeah, into x to the power 16. If it's something like that, you'll have to calculate something sometimes extra. But in general, uh, it's going to be definitely much better than n, because you're going to be saving on calculating quite a few numbers. So a very simple formula. So let's say you have to calculate x to the power n here, right? So double result equal to 1. Uh, bool is negative equals n is less than 0. If n equals 0, return 1. N equal to abs n. Apart from that, okay. While, so we're going to be doing this for some time now. Uh, so let's say n is a factor of 2. So if n percent 2 is 0, so we'll only need to calculate the so let's say answer is x. So we only need to calculate result equals result times equals result. And if it's odd, we do result time equals x. In this case, we won't need to calculate half the results. Hence, so you can look at n as the subspace, and here we're only using it once. So while n is greater than 0. Sort of from memory, because I have done this before. Might be a number of, or it's a test case. It's 2 to the power 10. Okay. That's taking more time than usual. Oh, okay. Let's take a small case where n is say 2. So result is x, and you just find x square. So it's gonna be a little extra. Let's do this and see. That's weird. Not changing x anywhere, right? Result is 2, n is 9, n is 8, result is 4, n is 4, result is 16, n is 1. What? Sorry. I am screwing up somewhere. Um, so let's keep another integer. Int k equals to 0 while k is less than n. Um, no, that's not gonna work. So basically, if n is divisible by 2, which means you reduce the power by half, so you'll multiply, so you'll get the square of whatever you're holding, right? Hmm. Let's put it like greater than 1 maybe. So it's 10 and 5, right? Oh, so it's not actually, yes, this is not correct, I think, because what's this doing is it's increasing result by x. So let's keep this number separate, I guess. So this is the time you'll have to multiply it separately because you removed it from the power, right? Okay, so let's keep another counter. Int int odd equals 0. Let's say odd plus plus. Let's not do this. N minus minus. If odd equals 2, odd equals 0, n plus equal to 2. Okay. So relative 4. Now to do 4 to the power 5, right? 4 to the power 5 is what you have to calculate, which is the answer. It's good enough. Now, since it's odd, odd plus plus, n minus minus, n is now 4. Oh, that never happens, I guess, inside the loop. Just cut this out and put it outside. That's it. So let me just write this down, sort of writing it in my brain. So it's say it's to the power 10. So you do 4, make it to the power 5. Now it's 4 to the power 4 into 4. So what I'm doing is making it 4 to the power 4 into 4 to the power 4 instead. So instead you need the way to calculate the other numbers separately. And maybe do this instead. Now just to check if it's going to be 0 or 1. Let's check minus 2. So for negative numbers, so it was 2, right? So you just have to do it once. It was 2. If it is 2, then Let's say if I started with 9. I started with 2. I have to do square. So this is separated. Then it becomes 16 to the power of 2. Becomes 256. 1. Yeah, it should be, I think, greater than 1. Then this will pass. Then I have to take care of 2 and 10. See why that would fail. Yeah, now to see why this is failing. X is this. N. So this is 2. This is 10. So you do 4 to the power 5. Separate this. 4 to the power 4 and this. Check is even. Yep. Then you do 4 for the 16. Square times 4, which you've kept separately. 16 square. Now n is greater than 2. Yeah. So 6, 6 is 30. So 256. Yeah, it should be 256 times 4. Or times equals not x but result. That's why I was failing. Okay, let's just submitting is fine now. Runtime error. If n equals int underscore uh, n equals to int underscore max. Int underscore max. And let me keep a flag. Int n int min equals false. This is probably a better way. I mean, probably this is not done in that case. Maybe some other check. Maybe we don't need to find the absolute in case we keep dividing at one point, or if n is less than minus 1. Let's see if that is enough to take care of everything. To 10. What about 2 minus 10? Let us see this. 4. Oh, this I think we'll have to check then. Stop is negative n plus plus else n minus minus. Yeah, yeah, this should be fine. Awesome. Let's just check. This won't work for int min. Okay, that's cool. Let's look at C++. Oh, seeing 5 different choices when talking to an interviewer. So this is recursive. Hmm. See, I told you about that other solution also, but you don't really need to worry about that one. No, that's okay. As nobody's doing this solution, which is also pretty straightforward. But never mind. I think the solution is that itself. Um, by name, I think this is some question that I've already done before. So you have to print it in spiral order 1 2 3 4 5 6 sorry 1 2 3 6 9 8 7 4 5, which basically is very similar to what the question we just did, which was coming from outside to inside. So over there we had a left and right border and top and bottom border, which is same as the left and right. In here we'll do the same thing. You start with the left border, you go to until the right border. When you reach the right border, you start going bottom. In the direction we'll maintain using a flag. You go bottom till you hit the bottom border, then you go left till you hit the left border, then you go top till you hit the top border, which is here. So you stop over here, then you start going right. When you start going right, you update the left border. When you start going left, you update the right border. You start going bottom, you update the top border. When you start going top, you update the bottom border. That way, you will never come back to an element and you will keep moving. So it's going to be n square. So you just do while iterator is less than your matrix length into breadth. And you just keep, you know, moving in the matrix. So really, really unnecessary to write it. Let's just find if there's a C++ solution. Yep. So let me show you. So this is the column is left and goes to right, plus plus, and break um, U less than D. Probably the borders, yeah, up and down. So basically, whenever you reach the borders, or you could have just done it for, you know, size times size, like m cross n, and then not checked for any of this. Yes, just um, go left to right, top to bottom, same. Then this is just basically updating the borders. Yeah, and that's it. So next time start from somewhere else. I think I'll show you where I've done this. This is arrays probably. Spiral. Spiral order matrix. Yeah, that's in JavaScript. So if you see what I did was push the item if the according to the direction. So it only took one loop instead of loops inside that. So what I did was change directions like this in if and else's. So if you read the right border, you start going down and change the direction. If you reach bottom border, then you change direction to left. If you reach left border, then you change this. If you haven't reached, then you keep going left. And if you reach top border, then you change direction to right. Otherwise, you keep going down. You print the arrow. Cool. Jump game. Given an arrow non-negatives, you initially positioned at the first index of the array. Each element in the array represents your maximum jump length at position. Determine if you're able to reach the last index. Okay. So there are two solutions of this that I know of that are fairly simple to understand and execute. The first solution that is the solution that I came up with myself without looking at the answers was using DP. So basically, you check at every point if you can make a jump from that point or not, starting from the end. So can you reach the last point from here? Yep. Then can you reach a point that is a winning point from here? So basically, this is equal to any solution. Is there any solution in front of it? And this is if there is any solution in front of it, which took a lot of time basically, and might give you TLE very easily. But a better solution that I found out was a single pass iteration through the array, wherein what you just do is you see what is the maximum distance you can cover right now from each point. And while iterating, you decrease the maximum distance, and if you find uh, if your maximum distance becomes 0, you basically return false. And if your index reaches last index, you return true. Um, and your maximum distance is updated every time by max of max and your wherever you are. So basically at 2 you start, your max distance is 2, you jump 1, you decrease max distance by 1, you calculate the new max distance as 3 a max of 3 and 1, so it's 3. So since 3 is greater than 0, you start moving forward. Now max distance is 2, you calculate the max of 2 and 1 is 2, you move forward again, max of 1 and 1 is 1, you move forward again, your index is the last index, hence you have 1. For this, if you see max distance 3, come here it's 2, come here it's 1, come here it's 0, hence you can't reach. Fairly simple, I think. This solution. To come to it, some of you might be able to, some of you won't. Let's write that down. So so okay. While I is less than nums dot size minus 1, int I equals 0. Break out of this loop when it becomes equal to the last index, right? Int max distance equals nums 0. If max distance equals 0, return false. Let's keep it as 0 instead. Max distance equals max of max distance and nums I, max distance minus minus, return true. Yep, it's that simple. TLE. Of course, this is something I always forget. I think you should just write it here, I++. Submit. Perfect. ON solution, ON space. Yep. Not sure. There's one other solution, I guess. I mean, one shortcut that you can add in this. That if max distance is equal to if max distance is greater than equal to nums dot size minus I, return true. So like say you have to reach here, right? So I is 0, size is 3. So if it's 2 greater than, I'll just remove it if it doesn't improve the time, but I think if for some cases it'll actually improve the time. Okay, it didn't, but I still think this is a good good condition to add. Merge intervals. Basically, merge overlapping intervals is the question. So 1, 3, and 2, 6. So 2 to 3 overlaps. So you combine them. I have also done this on IB and I saw the code as a matter of fact a few days back itself. Same example as well. And it's basically, let me show you. So you sort on the basis of the um, start value. So it was a vector interval here, and instead it's a vector of vectors. Uh, and this is A, and start we can call this 0. Also we can call this 0, and you have to replace interval by vector int everywhere. Just a vector. Hmm. Okay. So basically, since you sorted them from the start, if this if the second number is going to be a subset of this, then you store this the first of the first and the second of the second. If it's not, then you store first of the first and second of sorry, if it's a subset, then you store first of the first and second of the second. Otherwise, like in this case, if it's not subset, if it's partially overlapping, then you store the first of the first and second of the second. Basically, you store whichever is greater in case there is an overlap. And in case there's no overlap, you take the previous you take the previous you take the previous section, put it in your answer set, and then consider this as your new start. Okay. can go through this code if you want. Output this, expected was this. Why did this happen? Probably done something like this. Yeah. Yeah, so basically, like I said, you push the first if a dot size is 0, return. Yeah, so you push the first element, check if the start of the first, and you take a stack basically, and if the first element is less than the top of the stack, the first element, um, if the current element in A, which is this element, sorry, not the first element of the current interval is if it is less than your stack top. Now stack contains the ending of the previous. If it's less, which means it is going to get merged, and you take the top of the stack. If that top of the stack is less than this one, which means this whole thing is getting merged, and the answer is 1 6. So you push this in your answer. Else you push whatever you popped. If it's overlapping, uh, if this end is less than this, sorry, if stack top is greater than this, basically then this is getting merged. So your answer is going to be either 1 3 or 1 6. So if 6 is greater, then it's going to be 1 6. 6 is greater, then it's going to be 1 6. So you push 6. Else you push, if say there was 10 here, then you'd be pushing 1 10. Otherwise, say we have 1 6 right now on the stack. So in our next, when I is 2, it's checking for this one. We check what the top is. It's 8, since 8 is not greater than, not less than, is sorry, stack top is 6. Since 6 is not greater than 8, you come in this condition where you take the current stack and push it in a vector and add it to the result, and you push your new found items in the stack. Not sure of the solution, you can check connected components. Square sorting and log. So basically they take the merged intervals for all the intervals. They merge two intervals, else they update the end of your last interval. It's the same thing. Last interval they're getting from their answer. I was keeping a stack to keep the last uh, item. It's only gonna have like one item every time, so it's not very memory expensive. That's fine, according to me. Your interviewer might think differently, so it's him you have to convince, not yourself or me. Okay, cool. That's submitted. Yeah, awesome. Okay, I'll just do this in the background. I guess it's 1 a.m. over here right now, and I think we've learned quite a bit today. There's a few things on my to-do list for this channel. Number one is to make a sort of like a cheat sheet, which is basically I'm just going to use the then you can check that out. So I do have a lot of work at the office these days, but I will try to get as much content out as I can, especially the cheat sheets and also marking all the done questions. Hopefully, you'll have the done questions at least by tomorrow. And the cheat sheet, since I'm not going to be streaming on Friday, you will have the cheat sheet by Sunday. So that at least if anybody has an interview on Monday, they can use that. All right. All the best, guys. Keep studying.